Previous video we learnt about the concept of electric potential energy. So we took an example of, suppose two charges are there and two positive charges are there, and you want to bring the two charges together. So if you work against the repulsive force, a conservative force, this work that you do is get stored in a system, in this 2.2 charge points that we have, a system that's there. So it is stored as the potential energy. Now, what would happen if you release your external force? This stored potential energy would be recovered, right? Whatever work that you have done, that work, that external agent work has been stored as potential energy, and the moment you release that, the moment that you release that external forces, the work done was stored as potential energy, and it can be recovered. So it is reversibly working there. Well, if you generalize this concept and you take system of charges, then we can have a definition of what would be the potential energy of charges which is in a system, that is more than two charges when you have. So essentially I'm taking into account that electric potential energy. What would be the definition of electric potential energy of a system of charges? System of charges, or let's be more specific, system of point charges. System of point charges, and these point charges are fixed charges. Well, so what we can write as a definition? So we can write as a definition as the work done, the work that must be done to assemble the point charges is the electric potential energy, electric potential energy. So we are talking of energy here, electric potential energy of the system. So this is how we can define this, and we'll understand this by taking an example. Suppose there are fixed charges and they are placed in such a way that some external force is there, some unknown force is there, and as a result of that we have the charges. Suppose we have here Q1 and we have here in a form of a triangle, suppose here we have Q2, here we have Q1, and this we can have Q3, and the distances, suppose for simplicity let's take equal distances. And the distances is D. Well, so the work that must be done to assemble the point charges is the electric potential energy of the system. Now this work done, which is done to assemble the point charges, from where? From where? Here comes the question. So from infinite distance, from infinite distances, you have brought those charges and placed and assembled it, and that is what we are calling that it's the electric potential energy of this system. So the work that must be done to assemble the point charges in bringing from infinite distances, right? The assembly is happening by bringing those point charges from infinite distances at a point, at fixed points is the electric potential energy of the system. Now here's the situation. From infinite distances you have brought Q1, Q2, Q3. Correspondingly, we'll evaluate this and we'll try to figure out what is this interaction potential energy of the system. Another way of looking at it is that if you want to find this potential energy, this potential energy is exactly the interaction potential energy, right? Interaction potential energy. So this completes the entire concept. So let me walk you through again. What we are telling is, from infinite distances, you have brought these three charges and you have placed these three charges in this way, suppose, in a form of a triangle, wherein the distance between those three fixed charges is same. And what the forces that you have used, that is unknown, but we want to know what is U of this system, which is the potential energy of the system, or interaction potential energy, interaction. So all those charges are interacting. We have learned for 2-point charges, now we have here 3-point charges. So when we talk of interaction potential energy, what we are telling you is the total would be the possible combinations of the interaction potential energy. So suppose we name it this charge as 1, this charge as 2, or this charge as 2 and this charge as 3, then this U, the total potential energy, interaction potential energy, is the combination of 2 taken at a time. So it could be 1, 2 plus potential energy of 1, 3 plus potential energy of 2, 3. So these possible combinations we have taken, and when we sum it up, we are going to get this net potential energy, interaction potential energy that is there in the system. So with this information, we'll give values to those charges that we have got, and then we'll try to calculate and find out the value for it. So take note of these bit of essential concepts that is there, and then using this concept, we'll solve this problem to have the net potential energy of the system. Okay, so let me rub a part of it so that we move with the numerical values, and let me assign few values to it. So let us take this example. Let Q1, okay, and Q1 be a positive charge, Q2 be a negative charge we can take, and we can take Q3 also as positive charge. So suppose we take Q2 as positive charge plus Q, and we can take one as minus 4Q. So Q is any value that we have. We can define this Q, let Q equals 150 nanocoulomb, and Q1 is plus Q, Q2 is suppose minus 4Q, and Q3 is suppose plus 2Q. Okay, and the distance D that we have taken, so these are given values. So given values are, the distance suppose is 12 centimeter, and they are placed in this form of a triangle. The distances are equal, and now we want to find the net potential energy. So this net potential energy would be equal to U12 plus U13 plus U23. So we know this U, right? We know this U12, it would be 1 over 4 pi epsilon naught, and 12 means this and this, this and this, so it would be Q1 Q2 over D plus 1 over 4 pi epsilon naught it would be Q1 Q3 over D plus 1 over 4 pi epsilon naught 2 3. So 2 3 these two, so it is Q2 Q3 over D. So whatever is common we can take out. So we can take out this common thing and then we can sum it up. Well, now let's put in the values. So we put this outside the bracket. D is also common. So we can have this Q1. Now Q1 is Q, so it comes out to be Q times Q2 is minus 4. So this is minus 4Q plus. Then we have here Q1 Q3. So Q1 Q3. So it is Q times 2Q plus, then it is Q2 Q3, which is minus 4Q times 2Q. Well, so this comes out to be 4 minus 4Q square. This comes out to be 2Q square. This again comes out to be 8Q square. So we are getting here 1 over 4 pi epsilon naught. In the denominator also we have D, and in the bracket this comes out to be minus 4Q square plus 2Q square plus, and then it's going to be minus 8Q square. Okay, so minus 4Q square minus 8Q square is 12Q square, and then we have here 2Q square. So this comes out to be, so therefore you have, I'm writing it here, so from here it comes here, U is now 1 over 4 pi epsilon naught, and here we are getting in the bracket it is minus 10Q squared. This is what we get. So now if you put in the values, right, so therefore 1 over 4 pi epsilon naught is 9 times 10 raised to the power 9. This is the constant, which is 9 times 10 raised to the power 9. Okay, and it's going to be Q square, so meter square, this times meter square by coulomb square. So we can make the subject of the equation K. So we can get this force, which is Newton multiplied by meter square, and then coulomb minus square, right? So this is what we get, and Newton is also there. So this comes out to be minus, so we'll put the minus sign in the beginning. So here we have minus this times 10 times Q square. Now Q we are given 150 nanocoulomb, which is 150 times 10 raised to the power minus 9 coulomb square. So this is squared, and coulomb square. Now this coulomb square gets cancelled, so we'll be left out with this meter square here, and this is 150, and Newton is also there. So basically U is going to be in terms of joules. So U comes out to be, and over this we also have D, and D is 12, which is 12 meter. If you convert this into SI, it will be 12 10 raised to the power 2 meter. Okay, 12 raised to the power minus 2. So everything divided by 12 times 10 raised to the power minus 2 meters. So 1 meter would get cancelled, and then we can have this Newton meter, which is in joules. Well, let me rub this area and calculate the values. So let's see what gets cancelled out there. So we get here U as 9 times 10 raised to the power 9, and here it comes out to be 10 raised to the power 1 times 150 times 150 times 10 raised to the power minus 18. It will be 18, 9 minus 18 raised to the power, and it is 12 times 10 raised to the power minus 2. Well, whatever comes, it should be in joules. All are in SI units. Okay, so 3, we get here 4, and here we get 2, again 2, 75 times 75, and this comes out to be, this one gets one cancelled, so it comes out to be this, and here we get 9, and then we can use a calculator here to calculate it. Let me take the calculator here. So it comes out to be 3 times 10, so it is 3 times 75 times 75. All right, so approximately it's coming out to be 16875, and then it's raised to the power minus 9, and here it's going to be 10, right? So minus 9 is minus 8, and here we have here 2. So when it goes on top, so it becomes 3, and it comes out to be approximately 1, 2, 3, 4. So 3, and it comes out to be around 1.7. So this comes out to be approximately, minus is there, minus is the value which is coming up here, and this comes out to be minus 1.7 times 10 raised to the power minus 2. So we can express this in, this is in joule, so we can express this in millijoule to be minus 17 millijoule approximately when we calculate. So this is what we are coming after getting getting our calculations done. So it comes out to be 17 millijoule when you get this in terms of millijoule. Well, so here's the point. This point is essential to understand that this is a combination of all the possible combinations we'll work out, and then we'll put in the values and we'll get the result. So go step by step. It's very conceptual. We have applied that concept to this system of charges. So it's actually assembling of these charges at fixed locations. Okay, so what is that energy which is put in? What is the energy that's there? We have calculated this with the given values. Go through this, and in the next video we are going to learn about electrostatic potential, and then we'll come up with other numerical problems. We'll come up with electrostatic potential because of a dipole and other configuration. So watch the next video. Thank you.